Hello everyone, welcome to our lecture video. In this lecture video, we are going to explain how we can calculate deflection of beam using moment area method. We have already created lecture videos regarding how we can create deflection of beam using other methods such as Macauley's method, double integration method, parts of work method, which link you can find in the description box below. So in this lecture video, we are going to calculate how we can calculate the deflection of beam using moment area method. So in order to calculate the deflection of beam using moment area method, we are going to need some figures. So we have already done figures print. So first let's focus on this figure. So what we have over here is we have beam AB. So we're not going to focus much on the type of beam or type of loading. So what we need to simply know about is we have a beam AB, we have point M0 and N0, and all over the beam some sort of load is acting, and this has resulted in this type of deflection of the beam. And we have theta A, which is slope at point A, and theta B, which is slope at point B. And we have drawn tangent TA. This is our tangent TA, and this is our tangent TB. Tangent TA, tangent TB, and we have 2 points M0 and N0, and these are its corresponding point M and N in the elastic curve of the beam. Next we have a distance S up to point M0, and we have distance S dash from N0 to B, and we have a distance ds from M0 to N0. And over here what you can see over here is we have again drawn tangent TM for point M. It's our tangent TM, it's our tangent TN, and we have suppose the angle between M and N as d theta, and here we have our distance from here to here, from our Tn to Tm as a S test d theta. This is because we have our distance S test and we have our d theta, and we have simply used the formula theta equals to L by R. Since the distance ds is quite small, so ds plus S test is nearly equal to S test only. So we have simply used the formula of theta equals to L by R over here. So next we have the total distance from B to TA as D, and next we have what we have drawn over here is M by EI diagram, from point M0 to N0, and this is equal to distance ds. So this will be more clear when we will be explaining our moment area method. So we have basically two theorems for moment area method. Moment area theorem basically gives us two theorems, and we'll be focusing on those two theorems step by step. So firstly, I have explained all this figure, I have explained all the terms regarding this figure, and what we have done in this figure is, so now let's focus on this figure. So we have our M and N, this part of our elastic curve, this part of our deflected curve. So we have drawn it in and we have expanded this part over here simply. So what we have over is we have M, we have N. This is our deflected beam, and we have our tangent from M. So this is our tangent MTM, so our tangent MTN over here, and the angle between this is d theta. So what I didn't explain over is this is our theta AB. So this is our theta AB. So theta AB, what does theta AB means? Theta AB means simply it's our difference of theta A minus theta B. So what we have for theta AB, this is going to be our, so this is my theta A. So if I draw a horizontal over here, so let me just draw the figure a little bit more clearly over here. This is my theta AB, so this means theta A minus theta B. So I have my theta B over here, and this is my theta A over here. So let me draw, so in order to explain this clearly, so let me just draw it over here. So this is like over here is my, this is my, like this. So my theta A is actually this, and my theta B is actually this, my theta B. So my theta B is going to be from here to here. It's going to be a little bit larger angle. So if I draw my horizontal, so let's suppose my AB horizontal is like this, is going to be my theta B, and if I subtract my theta A and theta B, so this part is going to be my theta A minus theta B, and I'm going to write my theta A minus theta B as theta AB. This is not vast concept, so just for explanation, theta AB simply means theta A minus theta B, so remaining is theta AB. So now in this figure where we have drawn our expanded part of MN, what you can see is we have our tangent TM over, this is my tangent TM, and this is my tangent TN, and I have the angle between my tangent M and tangent N as d theta, and in this d theta, this angle is also going to be d theta. So as you can see here, while this beam, so this is a beam with the beam bends, we are going to have certain strain. We are going to have certain strain. So our strain, which means our del L by L, so we have a certain certain change in length over here, we have certain increase in length, and so certain increase in length over here, and we have suppose this horizontal increase in length as y, and we have our point n. So let me just draw this figure a little bit more clearly over here. So this is going to be my beam. So as my beam deflects with respect to the original position, so what I have drawn it from here, and we have drawn a simple perpendicular over here. So let me draw one more perpendicular over and just expanded the perpendicular upward, and this little increase in length we have with this will certain increase in length, and this angle is supposed as d theta. So as the beam bends, we are going to have certain increase in length. So this is a supposed increase in length. So we are going to use this for our theorem 1. So firstly, let's just move direct into the formula. So we have d theta. So we have our d theta over here. D theta means it's going to be perpendicular by base. So that's going to be our perpendicular. So our base is simply going to be this y, which we have supposed this particle length. This is going to be my y. So now for our this perpendicular portion, we need to focus a little bit more. So now for our perpendicular p, what we're going to do is we're going to use some of our small formulas. So we have our Young's modulus velocity E equals to stress by strain. So we have our strain E equals to del L by L. So we have our strain E equals to del L by L. So what we're going to do over here is our perpendicular is our del L. So also going to be increase in length, del L equals to E dot L, and our E is going to be, from this formula, our E is going to be sigma by E into L. So simply our perpendicular, which is our change in length del L, is going to write this as sigma by E dot L. Sigma by E dot L. So right now for our section MN, our length is ds. So we're going to, instead of L, we're going to write over here ds. So this is going to be, now we're going to use another formula what we have already learned from our beam is m by y equals to sigma by y equals to m by I. Sigma by y equals to m by y. So we're going to use this formula. So instead of sigma, we're going to write m by I. So let me drop this portion. So hopefully you have understand how p is equal to sigma by E dot ds. So we simply use this formula, and instead of L, we have written down ds. So now moving on. So now moving back here, sigma by E dot ds by y. So we have sigma equals to m by I dot y, and we have remaining as a ds by E, and in denominator we have y. So this y and y gets cancelled out. So we have m by ei dot ds. So this is our theta. So we have found our theta to be equal to m by ei dot ds to be equal to m by E dot ds. So our d theta is our this small part between m and n. So if we were to integrate this d theta from a to b, we are going to get our theta, which is going to be our total, which is going to be our theta ab. So if we were to integrate this equation d theta from a to b, we're going to get our theta ab. So integrating this equation, theta, this is going to be theta ab, integrate it from a to b, we're going to get m by ei dot ds. So as we have learned from our integration, this is going to give us our area. So so this is resembles as we are going to, this is going to L times b. So this is resembling as our ds. So let's move on to this diagram. So I have drawn the m by ei diagram. So this is how our m by ei diagram looks. So we have just supposed it is going to look like this. So it's going to start from 0 and end at 0, and it's going to be some up and downs between these points A and B depending upon the load. And this is our section from M to N. So you can see over here, this is our length ds. So this is going to be our m by ei diagram. So m by ei times ds. What we are right now getting from over here is m by e is our this diagram, and we are simply multiplying it by ds. So we're going to get area of this section, since our integration gives us area. So this is going to be theta. So what we are gotten over here is, so this is going to be theta ab. So this is what so let me write this is area of, this is our area of m by ei diagram. This is our area of m by e diagram. But what kind of area? This is an area between a and b. So how it's an area between a and b? Because we have multiplied by m by ei with ds, and this is our ds is our length between a and b. So this is going to be our first theorem. So let me just state down my first theorem. So if I so let me just state my first theorem. So my first theorem basically tells me that So my first theorem is that the change in, so you can note this down. So now if we were to write the conclusion of our first theorem, so what our first theorem of moment area method tells us is that the change in slope of tangent to the elastic curve, the change in slope of the tangent of the elastic curve, which means change in slope. So right now we have calculated, this is our theta AB. Change in slope means theta A minus theta B. So okay, theta A minus theta B. The change in slope of tangents to the elastic curve between points A and B. Change in curve, which means theta A minus theta B or theta AB is equal to the area under M by EI diagram. Area under M by EI diagram, which is our this area under M by EI diagram between these 2 points. So our basically our first theorem first theorem moment area doesn't give us any particular slope, but it gives our change in slope. So in our previous theorems we are directly calculating our slope, but right now we are calculating change in slope. So how we are going to use this to calculate our slope will be explained in our numerical in our next video, which link you can find in the description box below. So right now we're just explaining our two theorems related to moment area method. So this is basically our first theorem. You can note this down, note down this theorem. So next we're going to calculate our next we're going to explain our second theorem related to our moment area method. So before explaining about our second theorem related to moment area method, we need to know about this point D. So I want to explain before, but let me explain a bit more clearly about what our D resembles. So what our D resembles over here, our D is our distance from our point B up to TA, which is our tangent from A, which is from our tangent at A to this elastic curve. So our B is our deflection of point B, deflection of point B on the elastic curve from the tangent. This is from our tangent to the point A, to this to the tangent at point A, to the tangent at point A. The tangent is at this curve. So let me explain again. So D is simply our deflection of point B from our point from our elastic curve up to this point, and this point is our tangent from A, which starts from A, and this tangent is to this elastic curve. This is a tangent to the elastic curve, and it ends over here. It's our perpendicular distance. This is our perpendicular distance. So let me just move on to our derivation of second theorem. So our this is our D. So how we are going to calculate our this D is going to be equal to integration from A to B S dash d theta. So as you can see over here, this S dash d theta. So right now we are in order to calculate this D, so we have to integrate our S dash d theta from A to B. So as you can see over here, so let me use two markers to explain this. So while our d theta represents like this, our d theta represents, this is going to be my part S dash d theta, but as I integrate this from A to B, so we are increasing this d theta up to we are increasing this d theta. So simply we are increasing this d theta to theta AB. So as you can see here, as we are increasing, when we reach our maximum potential, when we fully integrated, we are going to get this D. We're going to get this D. So let me explain again. As we are increasing this distance of this S dash d theta, this d theta representing S dash d theta increases, and this reaches up to D. So we have understood how we have calculated the D using our method of integration. So next what we're going to do is as we calculate in our first theorem, d theta is equal to m by ei dot ds. I have already robbed that portion, so you can forward our video and see that d theta equals to m by e ds. So a dot b s dash, and d theta becomes m by ei ds, m by ei ds. So now, so as we explained before, m by ei ds and integration. So what does this represent? This represents our area. This represents our area of m by ei diagram into s dash. So right now we have got our d equals to area, which is m by ei into s dash. So we have got this as d equals to something of area into something of distance. So let's suppose this as d equals to a into x for now. So what does this refer to when we move to our m by ei diagram? So let me write down, so in order to explain this a little bit more clearly, first let me write down the second theorem. What my second theorem says, deflections limit of this part, we don't need it anymore. This is equal to ds, the deflection of point B. So right now we are going of point B, the deflection of point B, which is our D, which is our D of point B on the deflection of point B on the elastic of. So what our second theorem basically says is that the deflection of point B, the deflection of point B on the elastic curve from the tangent to this curve, from the tangent to this curve, or from the tangent to this curve at this point A is equal to the static moment. So right now we have calculated area into S. So I explained. So what we call the term when we have multiplied by area, this is called as moment. So this is called as moment is equal to the static moment about an axis through B. So whenever we are calculating the moment, it is about something, axis, or about a distance. So right now we are calculating from distance S dash. So distance S dash means, so what does our distance S dash means? It is from B. It means it is about an axis B of area under M by EI diagram between A and B. So basically what does this mean is, our distance D is simply going to be equal to area under M by EI diagram into S dash. So it's going to be static moment of this M by EI diagram. So static moment of this M by EI from this M by EI diagram. So it is going to be static moment of this M by EI. So for this, what we're going to simply do is we're going to multiply it by area of this M by EI diagram into a certain distance. So if we're going to calculate the deflection of point B, it needs to be distance from point B. And if we're going to calculate our moment of deflection of point A, which we'll be doing in our next example numerical, whose link you can find in the description box below, we'll be multiplying it with our distance from A. So in order to repeat this one more again, so our second theorem related to moment area method gives us idea about deflection. So it is going to give us our deflection of point B, which is equal to D, and this D is simply going to be equal to area under M by EI diagram, multiplied by the distance S dash, which is from our axis B. So simply to wrap up, our second theorem related to moment area method gives us of our deflection of point B, and this deflection of point B D is going to be equal to area under M by EI diagram. And this right now we're calculating deflection of point B. So our area is going to be from A to B. So we have from A to B. So area under M by EI diagram between A and B. So this is going to be our area between A and B multiplied by distance S dash, which is from our axis B. So this will be more clear when we'll be doing a practical example using both of this theorem. So you will be using this method to solve one numerical in our next video, which link you can find in the description box below. So hopefully you have understood the theorem related to moment area method. So if you have any queries, you can comment down below. If you like our content, do subscribe to support our channel, and do like the video and share with your friends. Thank you.